Okay. Okay. So we'll come to the next couple of things. So now what we'll do is this one is done. Now we'll try to figure out some tools which are this. Okay. So I'm sharing with you. Consider that you are having a protein. Okay. So you want to figure out what? You want to figure out that which kind of drug will be acted on it. Okay. So you did a primary research. You found that this is a protein. Okay. This is a protein in Mycobacterium tuberculosis which is responsible for its virulence. Okay. Understood? So what is the protein name? This is NADH quinone oxidoreductase. Okay, of what do you call Mycobacterium tuberculosis. Now why it is important? Because this enzyme, what it will do is it will oxidize all the quinone derivatives, among which many antibiotics are also there, and therefore make them unusable. Okay, so clearly understand. Here also we can see similar activity in this research paper. So here also there are some this thing entity which is acting as a redox reaction intermediate or something. Okay, so in this one what happens? This is NADH quinone oxidoreductase. As you all know, oxidoreductase is a protein or an enzyme which cannot act all its own. It needs a prosthetic group. Either it will use an NADH, either it will use an NADPH or an FADH. Okay, any of these this thing vitamin derived, water soluble vitamin derived, what do you call, prosthetic groups are needed for oxidoreductase enzymes. Now this oxidoreductase is important because it has the possibility to oxidize certain drug like compounds or antibiotics, and therefore making Mycobacterium tuberculosis what? To convert Mycobacterium tuberculosis as what? Who can tell me? Huh? What it can do? Who can tell me the consequence of this activity, of this protein's activity in Mycobacterium tuberculosis? Who can tell me? See how good is your this thing. So if this is the bacteria and this is a particular enzyme which is present inside the bacteria. Now what it will do is it will lead this bacteria to become something called drug resistant bacteria. Why? Because it will metabolize all the drug resistant bacteria. Okay, so because it will metabolize all the antibiotics, so इसको हजम कर लेगा, it will digest the antibiotic and it will have no effect on it. Okay, so this is the study you did. Consider that you have done a wet lab study where you have found out this particular strategy of this bacteria to become drug resistant. We have already discussed that drug resistant is a kind of what shall we say, this phenotype, drug resistant phenotype of a bacteria is a evolutionarily advantageous phenotype. Okay, advantageous phenotype. Okay, so if a single bacteria can get away with it, that no, it will multiply randomly and the whole what you call strain will become MDR. Okay, you must have heard about MDR TB. Okay, which our India is dealing with in a big way. So multi-drug resistant TB. Now your job is to identify how to make an inhibitor. Okay, how to make an inhibitor for this particular thing, particular drug. Okay, so you are about to design this inhibitor. Your job is to design this inhibitor. Okay, design this inhibitor. You have to design this inhibitor. Now there is a problem with bioinformaticians. What? They will figure out some coding strategy in order to give you an excellent result. Okay, or a like tool they'll design, and they'll identify a particular this thing strategy to make this design viable, or to identify an inhibitor. But many a times what happens, no, they are good at coding, but their biology is somehow this thing. And therefore, what they eventually do is, they come up with a design which is basically not reliable and not very practical in terms of biological world. Okay? And therefore, bioinformatics is still a biologist's thing, not a computer science's thing. Because the biologist will recruit the computer science people in order to make the computer science solution. But the biology will be very, very important. Okay? So here we should understand the rationale behind this we call as a rational drug design. So it is not a drug just like for the sake of the design. It is highly rational also. Okay? So rationality must not be lost. And therefore, previously we used to call it as simple drug design. But now, no, we are calling it as rational drug design. Why? Because many a times it has been seen that the drug has been designed, but there is no rationale behind it. Okay? So rational drug designing is very important. Now coming back to this particular protein. So this is our protein. Okay? So this is a GenPept format. Okay? We will convert it into FASTA. Now what we are trying to figure out? We are trying to figure out what are the unchangeable domains or very, very stable domains in the whole protein structure. So again, coming back to this, consider that this is your protein. This is your protein, okay? Out of the whole scenario or whole area, you identified that this area is such that it is highly hypermutable, okay? Hypermutable domain. Understand very, very critically, okay? Now, what is hypermutable? Means this area changes frequently. Sometime it looks like this, sometime this domain look like this, and sometime this domain look like this. Sometime look like this, sometime look like this, sometime look like this, sometime look like this. Are you getting? Can you see the drama? So what happens? This domain is hypermutable. Okay? As you can see, it is changing every time. So we will not target this region. We will target that region which is not mutable, not randomly mutable, and very, very stable. Let us consider this. This is a structurally stable domain. Structurally stable domain. And this domain, no, cannot be changed very randomly. And therefore, if I design a drug around this domain, okay, or this is a drug around that domain. So tell me which one will be more successful in the long run? Everybody should answer. So I am having two domains, structurally stable domain and hypermutable domain. So which domain will be more, if we target out of these two domains, which domain should be targeted for a rational drug design? Okay? Tell me. Which domain in the protein? The hypermutable area or the structurally stable area? We have to use the structurally stable area. We have to find out this drug structure, not that. This will be a better drug. Okay, this will be a better drug. Arey yaar. Oof. This is a better drug, okay? So we'll go to this particular area only. Okay? For that, we have to find out the structure, and then we should use this particular, what do you call? Sorry, what is that? No. What is that? Flow site. Yeah. This particular tool, very handy, a bit old, but very useful. It will give you an idea what are the hypermutable sites and what are the very stable sites present in the this thing, what do you call, this particular protein. So now we'll copy this and paste it here. Okay, and then try scan. So once we try scanning, it will identify me the regions which are highly stable in nature. And also the active sites of the protein. Okay. So this has identified a domain, this particular domain, to be the active site of the protein. So since it is the active site, it also is the stable site, and therefore we shall also, let us go for redisplay. Let's see what happens, if it can give something more. Okay. So since it is the stable site, we will design our drug around this particular domain. Okay, not the hypermutable domain. So for a preliminary identification of a drug-like ligand which is targeted to a particular protein or particular enzyme, we can use this pro site very efficiently. Okay, so this is one part. Then secondly, we can use one more domain or one more, what do you call, tool, which is this. Now Zhang lab is very famous lab who are using computational biology as their this thing forte, and it's a very famous lab which have designed a protein ligand binding site prediction. Now it has integrated multiple things. What is it has integrated? In this particular tool, we are using only a single consideration. What is the consideration? This is the consideration. We want a stable site which will not be mutated very randomly. Also, it could be the functional site of the protein also. And therefore, it is highly important to design the drug around this particular domain. So, we are having one more tool which will give us multiple, one layer more ability to predict. So what we'll do, we'll again add a FASTA of this protein to the server called coach, and then run the tool. Okay, so once we run coach, academic email is needed. Okay. Okay. So it will take a little time to figure out, but many a times if we give them common names, it will figure out the particular area or the particular domains which is available for drugs. Okay, it is something like this study that we did. Okay, just 1 second. If you can remember, we had a study. Uh, just hold on. Okay, so I'll just download this. So if you can remember, initially we had done a study where we downloaded one PDB and used one software to analyze it. Those who were not present, they can also see. So what we did here is, and many of you were already present. So what we did here is, this is the multimeric structure of a protein. If you can remember what we did, we changed the structure into a molecular surface. Okay, if you can remember. So it will take a little time to convert the whole protein into a molecular surface, and then what we did, we identified this particular area to be identified by a method called distance. Can you remember? It given us 1.5 angstrom, 2.3 angstrom, and so on and so forth. Okay, here also now we can do it, but since it's a very large molecule, it can give us uh, some uh, less precise results. Despite of it, we will give it a try. Okay, now what we'll do is, we will display distance. Okay, so now here you see what we are trying to do. Consider that this is an important pocket. Okay, we will find out the dimension of the pocket, and this software will easily give you the dimension in terms of angstrom. Now here you see 14.146.63 angstrom is the, what do you call, size of this pocket. Okay, so what does it mean? It means that if you want to build a drug around it, so if you want to build a drug around it, consider that this is your studied file. Undo, and then here. So your drug should have also at least this size, isn't it? Which is equivalent to the size of the pocket, isn't it? So this is how also our software, this software coach, will give you an idea. It will identify most of the available pockets and eventually give you very important specific pockets like this, which will be used for a drug to accommodate and therefore inhibit the protein. Okay, so these are some basic aspects of rational drug design. We will once again get back day after tomorrow, and we will complete these particular stages. Okay, for example, we will do about lead optimization and then docking. Okay, so in docking, what we'll do is, we'll literally do this. We'll identify a pocket, and then we'll try to figure out how good it binds with the pocket. Okay, many of you may already be aware. For those who are not aware of, they will surely have a good time. Okay, if you have some specific question, you can ask me. Okay, if you have some question, you can get back to me. Unless we are calling it a day. Okay, see you next.